Hi, this is lesson 13.1, displacement vectors. So we're going to try to do addition, subtraction, scalar multiples, and then resolve into components. The displacement vector from one point to another is an arrow with its tail at the first point and its tip at the second. The magnitude or length of the displacement vector is the distance between the points and represented by the length of the arrow. The direction of the displacement arrow is the direction of the arrow. So here's a vector. This is the equivalent vector right here because it has the same direction and the same magnitude. And so when we look at the length of this, the length is the magnitude. And then direction is just simply the direction. Sometimes we give the angle measurement. Sometimes you just look at it and see the direction. My drawing's not perfect there, but it's supposed to be the same length and same direction. And so that's what these are saying. These two vectors are the same direction, same magnitude. And so that's what we consider to be the same as a vector. Now we use this notation for PQ, so we start at P and finish at Q with the little arrow over the top to denote the displacement vector from P to Q. The magnitude is written as double bars around the V vector. And so that is the same thing as the magnitude. Now if we want to look at addition of the displacement vectors, what we can do is say, for instance, I walk in this direction 75 meters. Then all of a sudden I take and I turn and go in this direction for 50 meters. What is my resultant distance, or where am I? Well, the result then is going to be this vector right here. And so when we add these things, what we do is we say that we go tip to tail. So if I take the first vector and I go to its tip, which is right here, then I take the tail of the next one and go in that direction. So I just place one at the end of the other. Now, does it matter if I do this one first and then this one second, or if I do this one first and then this one second? No, it turns out that it doesn't matter. So if I go here first and then I go here, that's going to be the same as starting off by going here and then adding this one. I end up exactly in the same spot. This is my resultant vector, and so this is my finish line. We're going to be adding vectors by components, but you need to know the geometry of them as well. The difference, when we find the difference of two vectors, for instance W minus V, I can put the two tails together and then put a resultant vector over that. So that's what they did here. So if I take W minus V, so here's my W, and then I subtract off the V. I put the two tails together right here. And then how do you draw the tip? Well, the tip is going to go from, well, I should say the tip of your resultant is going to end up at your positive quantity here. Now this is one way to do it. The other way to do it is to say, okay, if I got my W like this, and then I'm going to subtract off my V. Subtracting the V means that I'm going to go in the opposite direction. So let's see if I can draw this fairly well. So now this is going to be the opposite of V. Now when we did this before, we said that we would add these two. And so this one is W, and so I want to do W plus V. I'm sorry, plus a negative V. So here's my negative V here. So what I got to do is I got to go tip to tail. So I can take this one now, and I'm going to move this one up to here. So here is my negative V. And so now if I do my resultant vector, that's going to be this one right here. Now if you notice this one right here, that should be equivalent to this vector right here, which it is. Okay, so a lot of different ways to do this, but if you want to find the negative V, you can go the tip to tail method. Otherwise, if you want to do this method, you can just do your two tails together and then make sure that your tip finishes with the vector that's positive here. So that's how you can subtract two vectors. Doing it with components is very easy. It's like algebra. Some things to note. We have the zero vector. We have to have the zero vector in order to do our algebra. So this is a displacement vector with zero length. So it doesn't have any direction either. It just has zero length, and you need that in order to do your algebraic manipulations. Now if we go down here, we got scalar multiplication. With scalar multiplication, if we have this delta is a scalar for us, and v is the displacement vector, the scalar multiple of v by, I said delta, this is lambda. Sorry, written lambda v is the displacement vector with the following properties. The displacement vector lambda v is parallel to v, pointing in the same direction if lambda is greater than 0, and in the opposite direction if lambda is less than 0. The magnitude of lambda v is just going to be lambda times, its absolute value of lambda, times the magnitude of v. So we can write this like this, if we wish. So here's some quick examples. If I have my v here, this is just going to be 2 times v, same direction, it's going to be twice as long. This is 1/2 of v, it's just 1/2 of v, same direction. This one would be negative 2v, because I can take this v and I can replace it over here and do it twice. I didn't kind of come out exactly right, but there you go. So then you can just do a scalar multiple if you want to magnify or dilate these things. Now on the lower right hand part of your page, we have addition and scalar multiplication of vectors in components. We can write vectors in component pieces, where we now do have this magnitude times this unit vector that we do have is I, j, and k. What's I, j, and k? Well, if we have the x and y axis, this is my x axis, this is my y axis, I is simply going to be the vector that is in the x direction, which is 1 unit long. So that this is your I vector. If I do the same thing in the y direction, I'm going to end up with this vector here, 1 unit in length. That's going to be your j vector. This is an I up here. Okay? And you can do the same thing in the z direction, and that's going to be your k vector. So then if we multiply them by a scalar, that's just going to push it out in the x direction for the I. This is going to push it out in the y direction for the j, and this one will pull it out into the z direction for the k here. And so here's just another vector that's written like that as well. If I want to add two vectors together, all I have to do is add their v1, w1, put them together, and I get my I. v2, w2, and I get my j. v3, w3, and I get my coefficient of my k. If you do a scalar multiple, you're just going to multiply everything through by that scalar. Okay, let's do some examples here. This one is just using some algebra to put this stuff together. This is a vector that's written with I and j, so it does not have a z component. If I want to deal with this, I can take this scalar and multiply by each one of those pieces of the vector, and I'm going to get 6i minus 2j. And then I can distribute this one amongst those, and I'm going to get I minus 2j, and then I'm going to get plus 3k. Now you just combine like terms, so I'm going to get 5i minus 4j plus 3k. Now I can do this in 2 dimensions pretty easy. I can't draw in 3 dimensions as well. But if I want to know what this 3i minus j looks like, I can do it in the xy direction. And so if I do my x, I do my y, I know that I have 3i. What does that mean? That means that I go out here by 3 units. That's going to be one piece or one component of my vector. And then I'm going to add in a negative j. Negative j means I'm going to go down by 1 right here. and I'm going to have this vector here. Now we said if we want to add these two, we want to go tip to tail. So I take that one and I put it on the end. My resultant vector is going to be like this. And so when I look at this vector, I have an x component of 3, and I'm going to have a y component of 1. That's exactly what this means right here. Now when I do this one, this is going to have an x component of 2, y component of 4, and a z component of -6. So you could start at the origin and you can go out to this point, and then that would be your vector. Now obviously I've simplified different things, and so this would be going out 5 on your x, 4 on your y, and 3 on your z-axis in order to plot this vector. So then you'd start at the origin and go out to this point. That would be your vector that you do have. Now some of you have dealt with vectors before, so you should be zooming through this. Some of you have not, and so this is all brand new for you, so you're going to struggle a little bit, but you should be able to pick some of this up. Now let's go to this next example that we do have. Find the value that a is greater than 0 such that u and v are parallel. So to be parallel, that means that their components have to be multiples of each other. So if I look at this, how do I get from this 3 to this -12? Well, I can do a scalar. If I'm doing, I know that they're parallel, so I need one multiple of another. I know that I multiplied this by -4. Let me put a dot there. So I multiply by -4 to get from one to the other. So that means that if I take -a and multiply it by -4, I better get out my a squared. So now what I can do is solve for this. This is going to be 4a is equal to a squared. A squared minus 4a is equal to 0. So I get a is equal to 4 comma 0. Now, which value of a do I want? Well, this is extraneous because a is greater than 0. So a needs to be 4. So I'm going to get this vector here, which is going to be 3i minus 4j. And then this one would be -12i. And this would be plus 16j. Are they multiples of each other? Yes, they are. So then they would be parallel to each other. If I drew these out in what we call standard position here at the origin, this one would be this vector, and then this blue one would be this vector here. So then it would just be 4 times the length, just in the opposite direction. So yes, they are parallel to each other. Or I guess you could say that they're the same line, but I got to double check, is that what we want or not? Let's run with it right now, and then we can double check and get back to you in class. Now here's this thing about resolving a vector. Resolving a vector just means that you put it in ijk form. And so if I have this vector right here, which is 3i plus 2j, if we want to resolve it, we already resolved it because it's I and j, but if I have this vector going to 3, 2, I have an x component, which is my 3, and times I, and then I have a y component with it, which is the 2 times j vector. Okay, so then that's resolving it into components. So for instance, let's do this example. If I want to resolve a vector v into components, if I know that the magnitude is 6 and then theta is equal to pi over 3. Well, this goes back to similar to our polar coordinates where we know this. So if I want to do the same thing here, what I can do is vector v is going to be equal to, I have one component that's going to be the magnitude times the cosine of theta. So this would just be 6 times cosine of pi over 3. This is my x direction, so that's going to be times I. Remember, I is 1, 0. That's that vector. Then if I want to finish this off, I'm going to do the same thing, but I'm going to go 6 times the sine of pi over 3. And I want to do that in the y direction. So if I want to put this vector into components, I got V is equal to 6 times the cosine of pi over 3 is going to be 3I plus 6 sine of pi over 3 would be 6 square root of 3 over 2. So it would be 3 square root of 3J. So there's your vector. Components of a vector, of displacement vectors. I can find components by just taking the difference of each one of the coordinates. So if I have a starting point P1 and a finishing point P2, I can just take the P2 points minus the P1 points, and that would give me each one of my components. So for example here, find the displacement of PQ if P is equal to this point and Q is equal to this one. So I'm just going to take the P minus the Q and put it into my vector form. So PQ is equal to, I got my -2 minus 1. I think you can see the rest of this. One thing I haven't been doing is putting the little vectors over I, J, and K, and I should do that. Because those are definitely vectors. Sometimes we call them unit vectors, but this is the form that we want to put this in, and then I can simplify this down. So I get -3I plus 5J plus K. Now what if we want to find the magnitude? How do we find the magnitude? Magnitude is just the distance. So I can use the distance formula in 3 space in order to figure this out. So here's where I talk about, well, I have it down here. For the magnitude of a vector in components, you just go ahead and use the distance formula essentially, as long as your vector is in standard position. If not, you got to take the difference of each one of the sets of coordinates and then square them. So my displaced vector is through the origin, I guess you could say, and that's what's happening here. And so I have each one of these values, and so then I just go ahead and take this. Here's my magnitude. This is how I write it. The magnitude of V, which in this case now is PQ, the magnitude of PQ is equal to the square root of -3 squared plus 5 squared plus 1 squared. Magnitude of PQ is going to be then square root of 35. So that's the length of that. Now I just mentioned that these are all unit vectors because they have a length of 1. What happens now though is that we want to be able to use different vectors that are of length 1 in order to manipulate them and use them later on. And so if it is off in this direction, what we can do is take this vector and make it of unit 1 length. So we want it in the same exact direction, but we want this length to be 1. And how we do that is we divide each one of these coordinates, each one of these, by the magnitude. And so if we do that, then that will make the overall length 1. So let's see how this works. So if I take the magnitude of my vector P, and I go ahead and find this, that magnitude is the square root of 21. Now to make each one of these vectors a unit vector, as we have up here, all you have to do is take each one of these pieces and divide by this magnitude, and that will put my vector at a length of 1. So if I want to do this unit vector, let's call it U, all I have to do is take my existing one, -1 over the square root of 21, I, and then plus 2 over the square root of 21, J, and then plus 4 over the square root of 21, K. Now, do you trust now that this gives me a vector of unit 1? Well, let's find the magnitude. The magnitude of U, well, you can do it. Try it. Hopefully you pause and try this. But if you notice, the numerators are exactly the same as what we just did. So this is just 1 plus 4 plus 16, which gives me the square root of 21. Square root of 21 added in the numerator, divided by square root of 21 is all 1. So then the length of this, or the magnitude of this unit vector, is 1, and that will always come out to be true if you just divide every piece divided by the magnitude. And they talk about it here. All right, this got a little lengthy, I apologize, but I had to do a lot of different things in here for you. And for some people, race through it, some people we had to go slow. Thanks for listening. I hope you have a great day. Thanks.